So today we are beginning lecture 73, and this is the review of all the lectures on stochastic methods. So this has been a really long chapter. We have gone from lectures 53 to 72, and we have covered a vast number of topics. So again, this is lecture 73 of the optimization series, and I'm Dr. Ranjan Ganguly. Now we see that heuristic and stochastic methods are becoming the method of choice for many engineering design problems. Now, beside the ones we have covered in this chapter, which include the genetic algorithm, particle swarm, SA, and finally ant colony optimization, there are a plethora of other heuristic methods which have come up. For example, we have the firefly algorithm, bat algorithm, bee colony algorithm, the electromagnetism based optimization, glowworm swarm optimization, and so on. So if you check around various journals dedicated to the topic of swarm optimization as well as heuristic and stochastic optimization, you will find that new algorithms are being continuously proposed. Now, one of the things which we see in all these methods is that they are typically based on some biology or science inspired heuristics. So most of them come from biological sources, but some are also inspired from science, which means physics or chemistry, as the case may be. And all of these methods essentially combine heuristics with stochastic search processes. So heuristics are simply rules of thumb which are written in a manner that they are a series of steps which can be programmed into a computer, and the stochastic process comes in through the use of random variables, populations generated from random variables, and basic decisions being made by the generation of random numbers. So these essentially lead to a particular characteristics of this method, that if you run these methods more than once, the result is always going to be different. So this is very different from the typical gradient based method, where essentially you run a gradient based method from a given point, you always get the same answer. So I mean, at least when you are using deterministic simulation. So that is the element of randomness which often helps this particular process. Now, it's also likely that more methods are going to be invented in the future, and people are going to find some inspiration from various aspects of biology and sciences, where most of the time some kind of optimization problem is being solved. If you look at most problems in physics, chemistry, or math, there is some minimum situation which is being solved. So generally nature prefers to have solutions which are some kind of minimization or maximization problems, and then solve these problems. Now, one of the things to keep in mind when developing any kind of new method or choosing new methods is whether the number of tunable parameters are lesser than existing methods or not. So we typically see that most of these methods have tunable parameters, and actually the lower the number of tuning parameters, the better this method is going to be for a broad class of problems. Now, the perfect heuristic stochastic method would be one which would not need tuning parameters, and we are not at that point yet, because most of the papers you will see published on this topic will present a certain method, and then they are going to apply this method on a variety of test problems, but then they are going to select certain tuning parameters to bring out the best results in the problem, and also they are often going to run their code 50 or 100 times and take the best possible solution. So these are things which people do, and then they come up with the best value. Now there's nothing wrong with that, but these kind of approaches are easier done in a university setting and more hard in an actual corporate setting. And therefore, if we want these methods to become popular in the industrial world, then we need to develop methods which have as less tuning parameters as possible. Now, stochastic optimization methods use random numbers along with heuristic rules to move around in the design space. This random part of the method lets these methods essentially escape from any local minimum point. So that is something which started the development of most of these stochastic methods, especially genetic algorithms, is that people were confronted with multimodal optimization problem where you have several local minimum point and maybe the global minimum point is considerably better than the local minimum points, and therefore it is very practically beneficial if we landed on this global minimum point, and that would then motivate the desire to use any kind of stochastic method or global optimization method. Now, as I mentioned, the heuristic or rules of thumb behind these methods is typically obtained from some concept in science where the search for a best or an optimal point is involved. And we'll see this is often the case in many problems in physics, chemistry, and especially in biology, that a perfect point is being sought by nature. Now let us go to the algorithms we have discussed. Now, genetic algorithms, they are based on heuristics which come from Darwin's theory, which is essentially dictated by survival of the fittest, and therefore there is a bias toward increasing the fitness in the next generation of the population. And essentially, this is accomplished by selection of a mating pool and then performing the crossing between the strings as well as mutation. So these are simulations of what nature actually uses. So based on that, binary GA used a binary representation of the design variable, and this led to very simple crossing philosophies and mutation schemes. Now, when people realize that many of the problems they are solving using GA are continuous and involve continuous design variables, then they figured out approaches to actually start with the real number based starting population and then effectively discover crossing and mutation techniques which can be used on real numbers, and this is led to the growth of real coded GA, especially as far as most continuous design variable problems are concerned. Now, in general, real coded GA is more useful for continuous design variables. Binary GA is better for discrete design variables. Genetic algorithms are good search methods if you want to find a global solution, but one of the problems is they tend to be slow. You need to perform a large number of generations for this method, and also they are very dependent on the starting population, the selection of the string length in the case of binary GA, and also they tend to get stuck every now and then. So this slow convergence property led to the motivation for development of some of the further methods which are based on swarm optimization. And philosophically, we also see that there was a change in thought from a purely Darwinian perspective, which is often the case with the simplistic life forms, to a cooperative type of perspective, which is often used by swarm type of situations. So again, there was some aim to develop methods which combine the good points about the genetic algorithm as well as local search and gradient based method. And one of the approaches, of course, is to start off with a GA, and then after some time when you are near the global minimum point, you switch to a gradient based method to converge rapidly. So that is probably one of the most useful hybrid genetic algorithm techniques which can be developed. There are also techniques which use gradient based or local search within the GA at each K, and there are also methods which may start off with some kind of gradient based methods from a plethora of points and switch to GA. So in these methods, I would say the ones which start off with GA and then switch to gradient based are more useful, and these can be generalized to all kind of stochastic methods. That you can start off with a population based method, find a region which is near the global minimum, and then you may start encountering problems in converging because the local search properties of these stochastic methods are not so good. At that point you may want to switch to the gradient based methods such as conjugate gradient or DFP or BFGS. Now, some of the methods we discussed are SA, which is another stochastic optimization method based on cooling a liquid very slowly to a solid crystalline state, and the method essentially comes from material science, or we can say physical chemistry or physics. There was also the method particle swarm optimization, which simulates the behavior of swarms. And these particle swarm optimization essentially combines the desire to reach the personal best goal while keeping in mind the global best of the entire swarm or the community. So this is often how higher life forms, including human beings, figure out how they function in the world. And so PSO brings out some of these cooperative aspects instead of purely looking at the competition aspects. Now both PSO and SA are good alternatives for GA for optimization problems involving multimodal functions, and generally recent literature shows a tendency to use PSO compared to GA, so there is a tendency in that direction. And one of the reasons is that PSO is also very simple. It deals with real numbers, and also it has a very simple mathematical formulation which can be coded in by people who have no background in optimization. So it is actually very simple. But it's important to realize that all these stochastic optimization methods based on heuristic contain several constants and parameters which need to be tuned for better performance. And the issue is that depending on the problem you are dealing with, you may need to have different constants and parameters. So many people who propose a stochastic optimization method, they test it out on a bunch of test functions. So there are many test functions which have been created by researchers through a long period of time, including by mathematicians. And these functions involve all kind of peculiar situations. They have local minima, global minima, they may have a huge number of local minima, and so on. So different types of functions are very important because you want your algorithm to work on these different methods. Now, one thing I would say is that most realistic engineering problems do not have the kind of pathological functions which you often come across in the mathematical test functions. So many of these methods will work quite well for most engineering problems which will probably have a mildly nonlinear kind of situation as we saw in the response surface case. But there may be peculiar problems which have deep global minima, which have a huge number of local minima, and in those kind of problems the appropriate selection of constant and parameters will become very important. So you may need to play around with these constant and parameters and run your code several times by changing these values, and then essentially pick the best solution you have obtained. Finally, we looked at the ant colony method, which essentially is based on finding the capability of ants, or simulating the capability of ant to find the shortest path between their nest and the food source. So again, a scientist named Dorigo looked at this particular thinking and developed the method which also led to the ant system. And this method also let us introduce the traveling salesman problem, an important problem in combinatorial optimization. And we saw how methods such as ant colony optimization can solve these quite intractable problems which are there in nonlinear programming. And there are many more methods beside ant colony optimization, but again, since this is a course, we have to limit ourselves to a certain number of methods. Maybe I will develop a later course where I will cover all the different stochastic optimization methods beyond what are discussed in this particular lecture. So at the end of this lecture, if you have gone through all the slides which I have put together, you will certainly gain a good knowledge of optimization. A lot of this content is present in my optimization book, which is published, and you can check that book out. And please give me your comments on the videos regarding how I can improve future lectures on this particular topic, or what you would want me to discuss in future as far as courses are concerned. So I will then terminate this course here, and I hope you had a good time here. I had a good time preparing this course, and I will see you in some different course on my channel. Stay tuned to my channel, and if you haven't subscribed till now, please do subscribe to my channel. Share the videos with people you know who may benefit from this particular situation. Remember, I'm putting up this material for free, so you can share it with people, and it can help us spread the field of mathematics and optimization in general to the large number of people around the world, and that is certainly going to lead to some kind of productivity increase and revolution in the community as far as the technical and engineering design people are concerned. Goodbye. See you in my next class.